Anyway, Brouwer and Cardinalities. Let me introduce it. It's about L.E.J. Brouwer, Dutch mathematician. Here are his dates, and here is the stamp that was issued in his honor about 15 years ago. Already 8 years ago, we had a Brouwer year in the Netherlands because it had been 50 years since his death. All kinds of things happened, and one of the things was a special issue for the journal Indagationes Mathematicae. It was dedicated to Brouwer. People asked me to write something, and I had no idea what to write about until I remembered that once when I was looking through some old books, I saw a paper by Brouwer with the title that you see up here, Die möglichen Mächtigkeiten, the possible cardinalities. I looked at it, I saw a strange sentence in there, and I thought, oh, I'll have to look at that again. Made a photocopy and forgot about it until I was asked to write a short thing for the special issue. I thought, well, maybe there is something in that paper. Well, the paper ends with a strange sentence, and this is the German original. Von anderen unendlichen Mächtigkeiten der Abzählbaren, der abzählbar und Fertigen und der kontinuierlichen kann gar keine Rede sein. Well, this is what it is in English. Of other infinite powers than the countable unfinished, and the continuous, we cannot speak. Okay, I had no idea what that meant. But I wanted to find out. And so I started to read the paper. Now, you can laugh about this, and I heard you did, and I did too. But I really wanted to find out what Brouwer was doing, because remember, Brouwer proved the fixed point theorems. He proved that the different powers of the real numbers were not homeomorphic. So he was no fool. And I wanted to know what this non-fool was thinking about. Say. Now, I'm not going to translate this whole German bit, but I am going to scratch a little bit here and there on these slides. Well, let's see. One of the things that this is roughly what I just circled is roughly translated underneath. Well, the opening sentence is also interesting. When one investigates how mathematical systems come about, one will find that they are built up from some primordial intuition of the two oneness. No, I don't know what that means either. But if you read further in the paper, you get some kind of idea of what is going on. And he also says that the intuition of the continuous and the discrete come together here. And why do they come together? Well, because one can think of a second not on its own, but well remembering the first. The first and the second are kept together. And then in parentheses, you see that keeping together is from the Latin continere. And so that's where the continuous comes from. The rest of the paragraph, I have no idea what that means. However, what about those cardinalities? Well, in the next bit, Brouwer gets a bit more concrete, so to speak. The intuition has the possibility to develop the order type omega. Before I continue, I think I had it on one of my first slides. This paper was something that Brouwer apparently talked about at the 4th International Congress of Mathematicians in 1908. And you can find it in his thesis, which I have here, although maybe you won't be able to see it. It's a very old copy of the thesis, and the whole argument just occupies a few pages. There's way more in the thesis than what I'm talking about today. Anyway, we can think of the order type omega, but okay, we would say, well, that's the natural numbers, done. But Brouwer indicates how we make the order type omega. When one thinks of the whole intuition as the new first, one can think of a new second that one calls 3, and so on. Well, the and so on, that's a little bit iffy, because whenever somebody says and so on, then they hope that we follow their and so on, but maybe we have another thought about the and so on. But anyway, Brouwer seems to allow for the natural numbers. Not only the individual natural numbers, and I'll come back to this in a moment, if I don't forget. But the other thing that the intuition also can develop is the order type eta. And for those of you who may not have seen this, this is what Cantor, in his work, when he talked about order types of linearly ordered sets, he says eta, that's the order type of the rational numbers. Whenever you meet that eta in this kind of context in papers from the beginning of the previous century, you can be pretty sure that it is about the rational numbers. Anyway, we can make the order type eta when one thinks of the intuition as a transit between the first and the second, then insertion has come about. This is my translation of the German original, and don't hold it against me if it's not quite correct. Again, this seems like individual steps, but Brouwer seems to think of it as a, how shall we say this, completed whole. So I'm looking for words because I'm trying to guess what Brouwer was talking about. But this, like I said, this comes from his thesis. The thesis was on the foundations of mathematics. This bit he talked about during this international conference. This was before he proved his fixed point theorem, his invariance of domain, and before he developed the index and the of mappings and so on. He was thinking really very hard, very deeply about what it means to do mathematics. And the only thing that he thought was pre-given was time. And a mathematician constructs things, and that construction has to happen in well-defined steps. And so the things that he tries to describe here are those steps that you use in constructing things. But almost, I would say, he sort of steps outside his boundaries, because both omega and eta, they require infinitely many steps. I mean, no matter how you think about this, you do need infinitely many steps to build omega and eta. So it seems to me that Brouwer seems to allow for infinitely many instances, and I would say that he would accept the actual infinite, because probably otherwise he didn't have enough stuff to work with. You know, as opposed to some people who, the finitists, who don't even like the actual infinity. Okay, what else is there that we can see? Well, everything constructed can be seen as a new unit, and this explains the richness of the infinite fullness of the mathematically possible systems. Okay, sounds wonderful. I'm not even sure what he means by that, but when you read the thesis, this is not so clear in the paper, by the way, but when you read the thesis, he describes steps that you can use to create, construct other things. Sometimes that makes for almost circular reasoning. I'll come back to that in a moment too. But his claim is that as far as discrete systems go, and whatever you mean by discrete, that's another thing, you can only build countable discrete systems. Discrete meaning as opposed to the continuum that we'll come back to in a moment. There is room for the uncountable, and we'll get to the meaning of that sentence about the cardinalities as we proceed through this talk. One can describe a method that creates from every given countable set in the system a new element of the system. Okay. And there are two claims. One can only construct countable sets in this way, as everywhere in mathematics. This is a limit that Brouwer imposes on himself. Many mathematicians, including myself, have no problems with pretending that we construct uncountable things in this way. Because, for example, if you say that from every given countable set in the system, you can create a new element, then I would say, well, if my system contains omega, then every countable subset of omega, well, meaning every subset of omega, can be used as an ingredient in this method. And I see uncountably many things appearing. Although you might say that in the system means that only the sets that we have constructed thus far can be used. And then, of course, at every given time, you have countably many. The next sentence, one cannot build the full system in this way because it cannot be countable. Well, really, this is a sentence that was not proven in the paper. It was just said it cannot be. And I think those are, we would say now, those are axioms that Brouwer imposed on himself. Okay, we cannot make, our full system cannot be complete because it cannot be countable, and that's sort of a given about the system, but it's not really a proof. At least I couldn't find a proof in the thesis, and I couldn't find a proof in the paper. But anyway, it is incorrect to call the whole system a mathematical set, for it cannot be built finished. We keep on going, building stuff, and We always have something countable, but it is never finished. Fine, that's his opinion. I'm not quite sure how to formalize this. And here is an example. The whole of the numbers of the second number class that's the that's the countably infinite ordinals. This is Cantor's term for the infinite ordinals that are themselves countable. The first number class is the natural numbers. The second number class is the infinite but countable ordinals. So in Brouwer's opinion, that's not a set. This was even I didn't write this in my slides explicitly, but this was even a proposition next to the thesis. In the Netherlands, you have to still, when you submit your thesis, you have to add a list of propositions that can be defended as well. And they should ideally not pertain to the thesis, but that doesn't always happen. But in Brouwer's list, number 13, if I'm not mistaken, there is the proposition Cantor's second number class doesn't exist. Okay, that's his theorem. I disagree, but never. The whole of the definable points on the continuum. The continuum, we'll get back to that in a moment. But if you look for definable points, well, you can keep on defining points. And in Brouwer's opinion, that is not a set. The whole of the mathematical systems, well, we would call it a proper class probably, but you cannot describe it in the way that he wants to. Okay, now here comes something that is mildly mathematical. And he talks about the continuum. Now, I found it a little bit odd when I read this, and when I read this more and again, and even when I read this in the thesis. The first part, here is the translation of what I just outlined here. We'll get back to the second bit in a moment. The sentence starts out with the continuum has the same value, the same rights as the discrete, but we can see it as a matrix of points or units and assume that 2 points are different if and only if they can be separated by a certain scale of order type eta. Okay, what this means, and there are more details in the thesis, that if you have a continuum, and when you read between the lines, you'll find that the continuum, as we would call it, is a linearly ordered set, dense with no jumps, so it's a compact ordered space. And the way you make the thing of order type eta is like this. You put something between any two consecutive points in your continuum. You just keep on going. This is what this interpolation means that we talked about a few moments ago. And in this way, we can put a scale, I don't know, a ruler, if you will, based on the rational numbers on the continuum, and we only call 2 points in the continuum distinct if there is a point from the scale between them. In the thesis, there is essentially an equivalence relation for points. That means that Two points are equivalent if they're always at the same side of the points in the scale. And so the equivalence classes would be intervals like these. Those will be identified to a point, and then we get a continuum with an everywhere dense countable subset. Now, the sentence that I outlined here and that I translated below says that the continuum is there. But if you, I'll get back to this in a moment, explain a few things. Well, is the continuum the real line? I guess so. Matrix, it's a source of points. It's, I mean, not the matrix in the sense of a rectangular array of points, not the matrix as in the movie, but the matrix, and this is what I lifted from the dictionary, a place where things are developed or formed. And the scale is some subsets of order eta. Now, a strange thing here, what I underlined there, one notices that the continuum defined in this way, so let me put the, let me underline this in the German and in the English. So in the beginning, it seems like the continuum was given. In the end, it seems like the continuum was constructed or defined. I'm not quite sure what to make of this. But I'll get back to this when I have some general remarks to make about what I think was going on there. So continuum exists, continuum defined. I'm not sure what that means, but in the steps that Brouwer allows for us in our construction work, there is one thing that we are allowed to do. That is, if we have a set of order type eta, we can envelop it, cover it, overlay it, if you will, with a continuum in such a way that the eta becomes a scale for that continuum. So there is a construction step here, and it constructs the continuum all at once. It simply says, here is the continuum, here is where we overlay it on the set eta. How? No explanation. Simply, it can be done. The reason that there is no explanation, I think, is that because probably Brouwer didn't conceive of the continuum as a set of points, but as a source of points. And so he probably didn't like Dedekind's construction, for example, with the cuts. I mean, you and I, in the modern way of looking at it, we would say, oh, we can do that. We take the rationals, we take the Dedekind cuts, there is our continuum. Done. But in Brouwer's time, in his way of thinking of it, the continuum was not constructed point by point, but more as a thing all at once. And I have no idea yet what that thing was supposed to be. Well, in the in the German here, one thing that I have it over here in the translation. When we are doing our work, we do countable steps all the time. And Brouwer says the continuum can never be exhausted when we use it as our matrix of points. Question, why can the continuum never be exhausted? Well, again, in the thesis, he mentions Cantor. He does mention Cantor's theorem that the real line is uncountable. And so I think with Cantor in the back of his mind, he says, well, the continuum can never be exhausted when you simply take out countably many points. How is the continuum defined? Well, that is still this open question for me. How is the continuum defined? And now I'm asking it in 1908, because that is when he talked about this at the international conference. I have no idea. But anyway, we have a construction step. We can complete a set of order type eta to a continuum. That is something that we can do. And now, and this is what the paper was all about, and this is also what those other pages in the thesis are all about. If we take a subset of the continuum, then it is either countable or of the same power of the continuum. And if this sounds familiar, this is the continuum hypothesis as formulated by Cantor himself. When you look in Cantor's work, there is this footnote or endnote in one of his papers where he says, using a method that I will not go into here, one can come close to the theorem that the equivalence classes that we get when we say two sets are equivalent if there is a bijection between them, gives us two classes, or it gives us finitely many classes of infinite sets, and actually two. And so this is what the continuum hypothesis originally meant. And then, of course, we ask ourselves, really? Because we know that the continuum hypothesis is undecidable. But let's keep in mind that we are following Brouwer's work, and we want to know what he was thinking. Well, so take a subset of the continuum, and here is the ultimate indication that the continuum really was just the unit interval, so to speak. Using some bijection or something, says we can assume that the subset actually lives in the unit interval. Why does he take the unit interval? Well, there is a countable set, he says, with whose help M is defined, but unspecified. But if you think back, you might sort of know what might be going on here. How do you define, how does a countable set help defining a set? And we'll get to some of the details in a moment. Well, if the countable set is of type eta, we can overlay it with a continuum, and you could say that that set of type eta helps to define that continuum. At least that's how I interpret Brouwer's writings. That countable set determines a subtree of the binary tree, because now Brouwer simply uses binary notation for numbers in the unit interval. And sort of judging by the way he writes it down, we take the binary tree, but we put it upside down, and the nodes in the binary tree are intervals of this form, a to a divided by 2 to the n, a plus 1 divided by 2 to the n. And M1 determines a subtree. What subtree? Well, all those intervals that actually intersect M1. And then we see, both in the paper and in the thesis, we see that he uses the Cantor-Bendixson process. We know what the Cantor-Bendixson process does to a tree. If you have a point And from this point on, there's only one branch going through that point, but through this point there are more branches passing through it. Then we simply cut this branch away because it corresponds to an isolated point in M1, and hence also to an isolated point in M if we read between the lines. And then we get a new tree. But in the new tree, there could be other things going on. There could be other points that determine a unique branch, and we take those away as well. Like I said, this is the Cantor-Bendixson analysis of the tree. And Brouwer, well, this will stop, sure, because we have only countably many points in the tree. So after countably many steps, this should end. We have two cases. The tree could be empty, but then M is countable. Why is M countable? Because it's the closure of M, and M is scattered. And because the tree is empty, actually the closure of M1, sorry, is scattered. That's how we would phrase it. Brouwer simply says M is countable because every point of M determines one of those intervals, and every interval determines a unique point of M eventually. And the other thing is, the tree is non-empty. But then M1 contains subsets of type eta. Because if you have a binary tree that is non-empty, and you cannot take away any non-branching, non-splitting branches anymore, then above every point there will be splitting branches. So the points will form a set of order type eta. Then M arises from such sets by overlaying a continuum. And this is where the paper is really unclear. And you have to actually read the thesis to get to the idea of what Brouwer wanted to do. You have your countable set, and you overlay that continuum. Let's see if I have it. Okay, I'll get to that overlaying in a moment. I want to finish with Brouwer's conclusion, and then we'll get to a few more things that can be said about it. So M arises from such sets by overlaying a continuum, fine. Possibly deleting countably many points. Where do those countably many points come from? Well, they are just mentioned in the paper, but in the thesis, he is a bit more explicit. It's more like, okay, we have two sets, and we build the set by overlaying we build M by overlaying the first set and deleting the second set, and both sets M1 and M2 are countable. And then the conclusion of the paper becomes, okay, there is just one power for mathematical infinite sets. That means the countable. Fine. One can add to these the countable unfinished. And the question is, what on earth is that? Well, you could say that Brouwer accepted the actual infinite because he accepted omega, but you could say that he sort of he went one step beyond the Greeks, so to speak. The Greeks didn't like the actual infinite, neither did Gauss, by the way. So they talked about potential infinite, something that was never finished. Brouwer likes that, but he doesn't like what we consider, say, omega 1, for example, the finished uncountable, or at least a finished uncountable. For him, omega 1 was always under construction, so to speak. It was never finished. And in general, countable unfinished is what he meant by, you take a method, you keep applying it, and you will never get to the end. And that kind of thing is countable unfinished, like the countable ordinals. And the continuous. Okay, and then of course, by this it certainly meant something finished, but only as a matrix, not as a set. It's a source of points, but we don't call it a set. So mathematical infinite stuff can be a set, then it's countable, or it can be unfinished, then it's a sort of a potential set, or it's also finished, it's the continuous. Fine. That is what Brouwer accepted as sets in 1908, or as sets, as available things. And of other infinite powers besides the countable unfinished, and the continuous, one cannot speak. Like I said, that's one thing that he told himself. Now, what do we make of this? And I'll get to the arguments again. Here is something that I found in Centraalblad, and you can actually get there because I put the slides on my website, and there are links to the various things that I'm using right now. But just by accident, I looked on Centraalblad, and I knew that it had older reviews than those of Centraalblad itself. And so this is from an older journal, but they incorporated it. And there was a review of Brouwer's paper. And I didn't translate this, but the reviewer confesses that what the author writes down here is not completely clear to him. So even in Brouwer's days, this was not quite clear. So he restricts himself to just reproducing the final words, and those are the words that we just saw in English. So the thing that I just mentioned in English, we have countable powers, we have the countable unfinished, we have the continuous, and we cannot talk about anything else. And if you, in the slides, click on this sentence, then it'll take you to the review. But I actually copied the whole review, so you don't have to go there anymore. Now, I already referred to the thesis a few times, because one of the things that was sort of not clear to me is, what do you do when you say have a nowhere than set of order type eta? That happens. For example, if you take a dense subset of the ordinary normal Cantor set, then that is full of holes. And how on earth do you overlay a continuum over that? Well, and the answer is you do it with holes, a bit like the Cantor set, but you leave out the left-hand endpoints. That doesn't make it connected, at least in our eyes, but it does make it a continuum as an ordered set. If you take the Cantor set and you leave out all the left-hand endpoints of the deleted intervals, so if in the first step of building the Cantor set, you do this, and then you keep on doing this, and you build the whole thing. And so all you are missing is that countable set of left-hand endpoints of those intervals. You end up with a linearly ordered set that is isomorphic to the unit interval. Because when you connect all these things here, so to speak, you end up building, you get a, if you leave out the left-hand endpoints of all the intervals that you delete from the Cantor set, then you can map that order preserving onto the unit interval by the Cantor, by the devil's staircase, if you will. So that is how it works, and it also explains how you can delete countably many points and still have a construction that will do something for you. Okay, how am I doing for time? Oh, fine. In the thesis, Brouwer really claims, well, this solves the continuum problem. I have proven the continuum hypothesis by adhering strictly to the insight one cannot speak of the continuum as a point set other than in relation to a scale order type eta. Okay, it's a bit strong, but in Brouwer's opinion, this solves the continuum problem. But how could we possibly read this when we disagree with him about, and I see that I still have a typo not accounted for. Brouwer allows him to construct countable sets, fine. Closed sets, because every closed set can be constructed in the way that that he described. You take a countable set, basically you take its closure, then you get a countable set that either can be overlaid with a continuum or not. And you can take their unions and intersections and differences, because you can always take stuff out, take stuff in, and whatnot. And so what we can say is that if we really want to, we can read the paper sort of as a proof that if you take the closed sets in the real line and you let them generate a Boolean algebra, then whatever you get is always countable or of cardinality continuum. So he proves the continuum hypothesis for the closed sets and everything that you can build thereof in finitely many steps. Interesting is that the way Cantor proved this as well. He proved the continuum hypothesis for the closed sets. And how did Cantor do it? Well, he showed that if you have a closed subset of the real line, and it wasn't scattered, so it did have a isomorphic copy of the rationals in it, take the closure, it looks like the Cantor set, it is more or less isomorphic to the Cantor set, and what he was able to do is use this isomorphism, homeomorphism, to map that arbitrary closed set onto the unit interval. So it is cardinality of the unit interval. Interestingly, what Brouwer did was make injections of the unit interval into those uncountable closed sets. So they were kind of dual in their way of proving this. Now, we could laugh about all those things that Cantor did, and we could laugh about me not understanding what was going on, but there is a serious point here. Brouwer was a young boy, almost, when he was doing this. He had ideas of how mathematics should be done and what it was. He tried to articulate that, and this was the first time he brought it out in the open internationally. He had written it in his thesis, and this 2 pages was what he gave to the world at the beginning. When you look at Cantor's work, you will, Brouwer's work, you will see that he kept working on this for the rest of his life, basically. And he was fine-tuning it and fine-tuning it and improving it and improving it and improving it. And he got many interesting results. Constructive mathematics grew out of this. So it wasn't a futile thing. It was really important for many branches of mathematics and science. For example, something that we all know, the infinity lemma of Koenig. It says, if you have an infinite tree with finite levels, then there is an infinite branch. Brouwer, in the same year as that Koenig proved his lemma, and we don't know who was first, Brouwer proved it also, but he proved the contrapositive. And it's known as the Fan theorem, which you cannot find on Wikipedia, by the way, but you will look, if you look for the bar theorem. No, sorry, you don't look for the bar theorem. You go to the Wikipedia entry for the infinity lemma, and you will find the Fan theorem described there as one of the equivalences of that theorem. But he proved the contrapositive, which is harder because he proved the contrapositive directly. How do we prove the contrapositive of the infinity lemma? We prove the infinity lemma itself. So we proved the contrapositive of the Fan theorem, and that is not what Brouwer would have wanted, because he didn't like the excluded middle. He didn't like proofs by contradiction or by contraposition. And in that paper, he proved that all functions on 0, 1, the unit interval, are uniformly continuous. And if you think that's weird, I know discontinuous functions on the unit interval, then you have to think twice, because those are not fully defined functions in Brouwer's opinion. If you say the function that is 0 below 1/2 and 1 starting from 1/2, that is not properly defined, because there are all kinds of real numbers that you cannot decide whether they're equal to 1/2 or less than 1/2 in the constructive spheres. So he had to do this constructively, and that is way harder than our easy proof of the infinity lemma. Now, to finish, there is an anecdote, and there is a reference to that on my website. And if you actually click on this line, you'll find the paper that that contains this anecdote. There was a meeting of the Dutch Mathematical Society. They used to have monthly meetings in some hotel in Amsterdam, and people were trying to explain to each other what Brouwer meant in some paper or another. And nobody noticed, but Brouwer entered the room. And after a while, he had looked at those people talking about his results. After a while, he couldn't hold himself back. He ran to the blackboard and he told them, "You have all misunderstood." And this is, I'll leave you with this. Because there was some problems, some things that make it very hard to understand what Brouwer's mathematics is or is supposed to be. Brouwer thought that mathematics was a purely mental activity. Writing it down was actually something that you shouldn't do. Of course he did, because he had to explain it to the rest of the world, but there was a sort of an important point that it was a mental activity, and that language was not good enough, not strong enough to explain what he wanted to do. And that is why the research in intuitionistic mathematics is still going on today, because people still don't know whether they understood Brouwer completely. So that is what I wanted to say today. Wednesday will be a little bit more mathematical than what I have today. And if you want some light reading, if you click on this link, it'll take you to archive.org, where they have the complete proceedings of this Fourth Congress of Mathematics. And you will be led directly to the whole paper. And this is a paper that I wrote about it, the one that I mentioned. It's in that special issue of Indagationes devoted to, dedicated to Brouwer. Okay, that's it. Thank you.